OpenAI is the leading AI company, and its recent iteration of models, the O1 series, is undoubtedly the most advanced AI currently available to us. Remarkably, this AI model has been kept under wraps to such an extent that if you ever dared to ask it what it was thinking about during the process of formulating a response, you'd be met with silence. The model provides a response that explicitly tells you never to ask a certain question again. If you keep asking it, you could potentially be banned from using OpenAI's services. This is surrounded by a lot of secrecy, as it marks a significant step toward AGI, artificial general intelligence, and many believe OpenAI may be the first company to achieve it. That said, there has been a lot of curiosity about how the system operates. And while OpenAI has released a few publications, none have fully revealed what's happening behind the scenes. Recently, however, a group of researchers from China published a paper that has us wondering, did they just unlock the secret? Chinese paper on O1. We need to understand how O1 functions and create a roadmap for building something similar. This paper delves into the scaling of search and learning, providing a roadmap to replicate O1 from a reinforcement learning perspective. If this paper proves accurate, it could be a game changer. It suggests that the playing field will be leveled, meaning that it's only a matter of time before other companies start developing AI models that rival OpenAI's in capability. I'll break this down into 4 parts, but first, let's take a step back and understand the fundamental principles behind how AI operates. One of the core concepts we have is reinforcement learning. To illustrate this, we can use a simple analogy. Imagine you're teaching a dog a new trick. You reward the dog with a treat when it successfully performs the trick. Imagine a dog that gets rewarded when it does something correctly. The dog learns to repeat those actions to earn more treats. And that's the foundation of reinforcement learning. In the case of AI, the dog represents a program. The treat is a digital reward. And the trick could be anything from winning a game to writing code. So, why is reinforcement learning crucial for the O1 series? OpenAI believes it's the key to making O1 so intelligent. It's essentially how O1 learns to reason and solve complex problems through trial and error. According to the paper, there are 4 fundamental pillars, which provide an overview of how O1 works. Essentially, we begin with policy initialization, which marks the starting point for the model. This phase establishes the model's initial reasoning capabilities through pre-training or fine-tuning, laying the foundation for how the model will operate. Next, we have reward design, which determines how the model is rewarded. We've already touched on this, but I'll go into more detail shortly. Then comes search, a crucial step during inference time when the model is thinking. This is how the model explores various possibilities. Finally, there's learning, where the model improves. This is done by analyzing the data generated during the search process. By applying methods like reinforcement learning, the model becomes better over time. The central concept here is reinforcement learning. The core mechanism that ties everything together is the interaction between the model, policy, and its environment. Data flows from the search results into the learning phase, and the improved policy is then fed back into the search, creating a continuous feedback loop. The diagram highlights this cyclic nature. Search generates data for learning, learning refines the policy, and so on. To truly grasp how this works, we need to first understand the policy. This serves as the foundational layer of the model. Think of it as teaching someone to play a complex game like chess. You wouldn't throw them into the game without preparation. Imagine playing a match against a grandmaster on their first day. You wouldn't just jump straight into the game. You'd begin by teaching them the fundamentals, how the pieces move, basic strategies, and perhaps some common opening moves. In a similar way, this is what policy initialization is for AI. For a powerful AI like O1, policy initialization provides it with a solid foundation of reasoning before it dives into tackling complex problems. It's about equipping the AI with essential skills and knowledge that it can build on later through reinforcement learning. According to the paper, O1's head start is likely divided into 2 key stages. The first phase is pre-training. This is where the AI is trained on a vast amount of text data. Imagine letting it read through most of the internet, or at least a huge portion of it. During this stage, the AI learns how language works, how words relate to one another, and acquires general knowledge about the world. It's like learning grammar and vocabulary, absorbing basic facts before attempting to write a novel. In this phase, the AI also starts developing basic reasoning abilities by working through the data. Then comes the critical part, fine-tuning with instructions and human-like reasoning. This is where we teach the AI how to reason and solve problems more specifically. Two key techniques come into play here: prompt engineering and supervised fine-tuning. Prompt engineering involves providing the AI with carefully designed instructions or examples to guide its behavior. For instance, the paper mentions behaviors like problem analysis, restating the problem to ensure the AI understands it, and task decomposition, where a complex problem is broken down into simpler steps. Essentially, we encourage the AI to think in a step-by-step manner. Supervised fine-tuning, SFT, is the other component, where the AI is trained using examples of human problem-solving. It learns the right way to think and reason by observing experts and their thought processes, step by step. Let's dive into something really fascinating. This is where design truly gets rewarded. The image you're seeing on the screen showcases two distinct reward systems in reinforcement learning: outcome reward modeling, which we have here, and process reward modeling, PRM. Let's break it down. Outcome reward modeling is pretty straightforward. It evaluates the entire solution based solely on the final result. So, if the final answer is wrong, even if most of the steps leading up to it are correct, the whole solution gets marked as wrong. In this example, even though several steps are right, the incorrect final outcome means everything gets flagged as wrong. Now, here's where process reward modeling really shines. PRM looks at each step of the process individually. It rewards the correct steps and penalizes the incorrect ones, providing much more detailed feedback. This feedback loop helps improve the learning process as it guides further refinement during training. For instance, steps 1, 2, and 3 are correct, so they receive rewards, while steps 4 and 5 are incorrect and are flagged as errors. The beauty of PRM is that it doesn't throw out the whole solution just because of one mistake. It pinpoints exactly where the errors occur, allowing for more focused corrections. This diagram really underscores how crucial process rewards are, especially in tasks requiring multi-step reasoning. They support continuous improvement and ultimately lead to better learning outcomes, something that's clearly central to what they believe ORM is all about. This is where things get really interesting, because this is the point where we dive into search, a concept that many believe could lead us to superintelligence. I recently came across a tweet that captured this idea, and I'll make sure to display it on the screen. When we break this down, we're essentially looking at AI thinking. So, when you have a powerful AI like O1, it requires time to process, explore different possibilities, and identify the best solution. This thinking process is what the paper refers to as search. To improve performance, they suggest that one way to enhance this is by thinking more during inference. This means instead of generating just one answer, the AI explores multiple potential solutions before selecting the best one. Think about writing an essay. You don't just write the first draft and submit it. You brainstorm ideas, write several drafts, and revise and edit until you're satisfied with the final product. This process is a form of search as well. There are two primary strategies in the search domain, which the paper suggests AI like O1 could use during this thinking process. The first is tree search. Picture a branching tree where each branch represents a different choice or action the AI could take. Searching is like exploring the tree, following various paths to see where they lead. For example, in a game of chess, an AI might consider all the possible moves it could make, then all the possible responses its opponent could make, and so on, building a tree of potential outcomes. The AI uses a specific set of criteria to determine which path to continue exploring and which one to prune, focusing on the most promising options. Essentially, it's about evaluating where to go next, what decisions to make, and which ones lead to the best rewards. It's like a gardener selectively trimming branches to direct the growth of a tree. A simple example of this is best-of-n sampling, where the model generates a set number of possible solutions and selects the best one based on certain criteria. In the bottom right corner, we have sequential revisions. This is similar to writing an essay, where the AI starts with an initial attempt and then refines it step by step, making improvements along the way. For example, an AI might generate an initial solution to a math problem, then check its work, identify mistakes, and revise its answer accordingly. It's like editing your essay by catching mistakes and improving it with every revision. You also need to consider how the AI decides which paths to explore in tree search, or how to revise its solution during sequential revision. The paper outlines two types of guidance: internal guidance and external guidance. Internal guidance refers to the AI using its own internal knowledge and calculations to steer its search. One example is model uncertainty, where the AI can assess its confidence in parts of its solution, focusing on areas with less certainty, exploring alternatives, or making revisions. This is like double-checking your work when you're unsure if you made a mistake. Another example is self-evaluation, where the AI can assess its own work, identifying potential errors or areas to improve. This is like having an internal editor that reviews your writing and suggests changes. External guidance is like receiving feedback from the outside world to guide the search. One example is environmental feedback, where AI interacts with a real or simulated environment and gets feedback on its actions. For example, a robot learning to navigate a maze might receive feedback on whether it's getting closer to or farther from the goal. Another example is using a reward model, which provides feedback on the quality of various solutions or actions, guiding the AI towards better outcomes. It's like having a teacher who grades your work, pointing out what you did well and where you need to improve. In essence, the AI learns from both internal and external sources to improve its decisions and actions. Search is the method by which 01 explores different possibilities and refines its solution. This process is guided by both its internal knowledge and external feedback, playing a crucial role in O1's ability to tackle complex reasoning tasks. While search represents how the AI approaches a problem, the key to its improvement lies in learning. The paper suggests that 01 enhances its performance through a powerful technique known as reinforcement learning. In this context, search generates the training data. As we discussed, search produces multiple potential solutions, and these solutions, coupled with feedback from internal or external sources, transform into valuable training data for the AI. Imagine a student preparing for an exam. They practice by solving various problems, receive feedback on their answers, and learn from their mistakes. Each attempt, whether successful or not, provides valuable insights that help them improve. Now, there are two main learning methods explored in this paper, and they focus on how AI learns from search-generated data. The first method is policy gradient methods, such as proximal policy optimization, PPO. These methods are a bit more complex, but the core idea is that the AI adjusts its internal strategy or policy based on the rewards it receives. Actions that lead to high rewards become more likely, while those that result in low rewards are less likely. It's akin to fine-tuning the AI's decision-making process through experience. Next, we have PPO, which is a well-known policy gradient method. PPO stands out for its stability and efficiency. It's like a careful, methodical approach to updating the AI's strategy, ensuring that changes don't happen too drastically after any single experience. Lastly, there's behavior cloning, which is a simpler method where the AI learns by mimicking successful solutions. If the search process discovers a high-reward solution, the AI can learn to replicate it in similar scenarios. This method is similar to how a student learns to solve a problem by studying a worked example. 01 might utilize behavior cloning to learn from the best solutions found during the search, effectively incorporating them into its repertoire of successful strategies. Alternatively, it could serve as an initial method to warm up the model before employing more complex techniques like PO. Now, of course, we have iterative search and learning. The true power of this approach lies in combining search and learning in an iterative loop. The AI searches for solutions, learns from the results, and then applies its enhanced knowledge to conduct even better searches in the future. It's like a continuous cycle of practice, feedback, and improvement. The paper suggests that this iterative progress is crucial to one's ability to achieve superhuman performance in certain tasks. By consistently searching and learning, the AI can overcome the limitations of its initial training data and potentially uncover new and better solutions that humans haven't yet conceived. With all of this in mind, now that we've covered how 01 works and understand its key pillars, Do you think we're close to achieving superintelligence? After reading this research paper and grasping the fundamental details of how Zero One operates, I think I truly understand why the wider AI community. It's not unreasonable to think that superintelligence could be closer than we realize. If an AI can search for solutions, learn from the results, and apply that improved knowledge to perform even better searches in the future, we would have a continuous cycle of practice, feedback, and improvement. In theory, this could lead to superhuman performance. So perhaps artificial superintelligence is not as distant as we might think. I'd love to hear your thoughts on this, and I hope you all have a great day.